Hello to everyone. My name is Stylianos Tsilioukas. I'm a PhD student at the University of Thessaly and the National Observatory of Athens. And today I'm going to present a new dark energy model, the Wald Gauss Bonnet topological dark energy model, and its potential to alleviate the H0 and sigma8 tension. I will begin with a space-time thermodynamic conjecture. It's a non-conjecture that we have some entropic models of gravity from which we can derive Friedmann equations and some modified cosmological scenarios. I will briefly review the normal procedure, the standard procedure. If we draw an analogy from black hole thermodynamics, and if one applies the first law to the universe apparent horizon, which will we denote by mathematical H, one can obtain the Friedmann equations. The steps are, the steps are these. If one starts from the apparent horizon radius, defined like this, the temperature, and the heat flow crossing it. This is a very known work from Kai and Kim. And the heat flow crossing the apparent horizon. And then, if one assumes that the black hole entropy is the known Hawking entropy with the area law, and substitutes all these quantities in the first law of thermodynamics, and then integrates, then one gets the two Friedmann equations, where something important to point out is that lambda, the cosmological constant, appears as an integration constant, nothing more. And on this basis, a lot of entropic models have been developed that yield modified cosmological scenarios when one changes the standard entropy relation, and maybe you can have another, if you put another entropy expression like Tsali's entropy or Kanyadakis entropy, then you get from this procedure new cosmological scenarios, new Friedmann equations. What we have explored in our work is that we will extend the entropy to the Wald Gauss Bonnet entropy. And we will discuss the scenario, the cosmological scenario that comes from this procedure. Now, if someone starts from the Einstein-Hilbert axiom, then one will get the Hawking entropy law. If the action in 4 dimensions is extended up to the Gauss Bonnet term, then, as Wald has shown, the entropy will be also extended by a new term. So, if we extend the action up to the Gauss Bonnet term in 4 dimensions, then, according to Wald, the entropy will be the standard Hawking relationship plus a new topological term, where T here of H, H is the black hole horizon, and C is a known topological index, the Euler characteristics that defines the indexes, the topology of the horizon. The horizon is an S2 sphere, so the Euler characteristic is 2. Now, it has been known for some time that this entropy, Wald Gauss Bonnet entropy, has an interesting feature, an interesting ambiguity, is that during black hole mergers, according to this entropy, the second law is the second thermodynamical law is violated, because when we have a black hole, two black holes that merge, at the beginning, before merging, we have 2 horizons, but after their merge, we have a deformed horizon. There's only one horizon. For example, we have 2 spheres, and now we have a deformed 1 sphere after that. So this new term, this topological entropy term, according to this one, we have a decrease in the Euler characteristic during a black hole merge. And according to, let's go back, and according to this, the Wald Gauss Bonnet entropy, due to this term here, since the Euler characteristics decreases, we'll have an integer instant decrease of the entropy. So there is a problem that during black hole mergers, according to this entropy, Wald Gauss Bonnet entropy, we have a violation of the second thermodynamical law. So this was like a motivation to investigate how the second law violation could be reconciled through a new procedure. And we have, and vice versa, I would like to say that if you have a black hole formation from a star collapse, then you have an increase, vice versa, an increase of the Euler characteristic and an increase of entropy. Now, a way to resolve the second law violation is by demanding that the topology of the causally connected boundaries remain constant. So, imagine that we have the apparent horizon, which is the outer boundary, the causal boundary of what's happening inside. And inside it, we have a black hole formation, black hole horizon formations, and black hole mergings. So if each time, what this proposition means, it means that if each time a black hole is formed, then two puncture disks open up in the apparent horizon. Then the total topology, the total topology and the total topological entropy will remain constant. There will be no violation, no total decrease or increase. So, and vice versa, when two black hole horizons merge, two of these puncture disks will close up on the apparent horizon. So, in that way, by demanding that the topology of the causally connected boundaries remain constant, that means that this will, that the Euler characteristic sum of the apparent horizon and the internal horizons will be constant. That means that every time that black holes are formed and black holes merge, then there will be a change in the apparent horizon Euler characteristic according to the active black holes inside. The active black holes are the ones formed and the ones minus the ones that merge that are inside. So in that way, the second law violation is resolved, and we have a new interesting aspect that the apparent horizon becomes topologically dynamical, and this produces, according to the space-time thermodynamic conjecture, this produces modified Friedmann equations. So, if instead of the standard Hawking entropy relations, we implement the Wald Gauss Bonnet entropy, and we follow the procedure and substitute to the first law and follow the standard procedure, then we get the Friedmann equation with a new correction term here that depends on the rate of black holes being formed or merged. And we can rewrite the Friedmann equation in the standard form and absorbing this term here, the dark energy term, to the dark energy density, where we can see that we have the standard dark energy with a lambda constant minus or plus a new correction term that depends on the rate of black holes that are formed or merged inside the apparent horizon. So, in order to calculate and evaluate the model, the first thing to do was to find a way to calculate the rate of black holes that are being formed or merged. To do that, we started from the star formation rate, best fit, model of Maddow and Dickinson. This is one of the best models because it's totally based on measurements. So there's a best fit model on the measurements. And according to the star formation rate, we were able to estimate the active number of black holes per redshift inside the apparent horizon, where we have some astrophysical parameters that have been absorbed in here. Like F binary is the fraction of stars that are in binary systems. F black holes is the fraction of stars that become black holes. The average progenitor mass of the stars forming black holes, and the fraction of the black holes that actually merge. So these astrophysical parameters are not free parameters. They have been estimated and constrained. I'll show you a bit afterwards. They're not free parameters of the model. So we reach now the Wald Gauss Bonnet cosmological scenario, assuming a flat universe and inserting the expression from the active black hole rate that we showed before. We arrived at this Friedmann equation, the dark energy density, and the equation of state parameter, where we have tilde A is the Gauss Bonnet coupling constant, which is the free parameter of the model, and C, where we have absorbed all the astrophysical parameters who are not free. They are estimated, they're bounded, as I will show. We have this integral here that fortunately it can be evaluated analytically by a hypergeometric function. And this is the involved parameters according to the literature. They are their bounds, assuming a Gaussianity and taking their mean values. We can now make a first assessment to the cosmic evolution of the modified Wald Gauss Bonnet scenario for a positive coupling constant. I repeat, this is the free parameter of the model. We see that the thermal history remains the same as Lambda CDM, the same. And we can see that the track energy equation of state has a slight phantom behavior. And for a negative Gauss Bonnet coupling parameter, we have almost the same thermal history, and we have a Kuntenses-like behavior that because of it depends on the star formation rate, there's a peak of this behavior at almost redshift 2. These are the parameters, cosmological parameters we have used, they're the standard ones. And now a preliminary assessment to see if the model can alleviate the H0 tension. And we can see that for different values of the Gauss Bonnet coupling parameter, while in high redshifts, we have the same behavior as Lambda CDM. When we go near the present time, we can see that for a bit higher values of the parameter, the H0 tension tends to alleviate here. And we have also made an analysis from another parameter inside its observational bounds, the black hole fraction, the fraction of stars that become black holes. And we see that according to this parameter also, there is the potential to alleviate H0 tension at present. And these are the corresponding dark energy equation of state, where we can see that for the phantom behavior, we can see that the Hubble tension is elevated. For the positive Gauss Bonnet coupling constant, and yes, I should say that before that, only for the positive free parameter of the model, we have this behavior, the phantom behavior, that it's known that it can alleviate H0 tension. Now we have made further analysis to constrain the modest parameter space, we use the Cobaya code on Supernovae Type 1 and Cosmic Chronometers. And we see that it alleviates the H0 tension with, and the MC procedure gives an parameter that is inside the bound that we have used it in the foregoing in the previous analysis, in the previous diagrams. And now, lastly, and this is the analysis of the parameter space about this parameter A that has the tendency to alleviate H0 tension. Now, but the sigma8 tension, this is a really first preliminary analysis. A lot of work has to be done. It's just a hint. And because in this model, energy does not cluster. So the modifications of the overdensity evolution will be given by the standard equation. And we can calculate the observable F sigma8. And according to this, we can see that during the present time, the late times, in comparison with Lambda CDM, which is a solid line, the model has the tendency to go to lower F sigma8 values. So this is really a first assessment, first analysis. Much more work must be done to see what happens with the sigma8 tension. This is a work that we are going to do in the future. Yes. So, in the conclusion, the Wald Gauss Bonnet scenario has some indications, has the potential to address the H0 and sigma8 tension. And the publications that we did regarding this work are these: topological dark energy for black hole formations and mergers. I didn't write the author's names. It's me, Tsilioukas, my supervisor, Emmanuel Saridakis, and Nicholas Petropoulos. And a second work that it's been under reviewed with using Wald Gauss Bonnet topological dark energy to alleviate H0 and sigma8 tensions with Maria Petronikolou and Spiros Vasilakos and Emmanuel Saridakis. Thank you for your attention.
Thank you very much. Any questions?
Thanks for the talk. I have actually only one question about the punctures, introducing punctures into this space-time to save second law of thermodynamics. But in that case, for saving second law of thermodynamics, right? For merging the black holes, I mean, it makes the Euler characteristic changing,
yes,
right? Then second law of thermodynamics in that case is in danger. So there are some punctures that you have introduced into the space-time in that case. But I mean, if there are punctures, which means that you introduce boundaries into the space-time. And in that case, to get the correct evolution equations, I think you should also consider the Gibbons-Hawking-York boundary action coming from the boundary, right? So I think the equations will change if you approach from this topological side. The equations will not exactly be the form of Friedmann-Robertson-Walker type.
Okay, I understand. You are saying that since we introduced the puncture disks, there are boundaries in space-time, so the Hawking-York term will come into play inside the equations. That's a very interesting aspect. We will look into it.
Yes, I mean, one should, in that kind of thermodynamic approaches, should be considered these boundary effects. Actually, it makes some think, for example, for entropy, it works to save the second law of thermodynamics. I mean, but on the other hand, it makes the field equations in the side of GR, for example, can make different.
This is, I think, this is very interesting. Maybe we should look at how the field equations of GR with these boundaries, how do they behave, and see if it's consistent, or what else they yield. Thank you very much.
Okay, any other questions?
Thank you for the interesting talk. I know nothing about it. I just want to understand the physical meaning. So in your talk, it seems to say that the merger or emerge of the black holes will kind of affect evolutions of the universe. Is that what you're saying? And the question is that if there are so many black holes to cause this effect on the universe, have you estimated how many black holes there are, and would it cause some even more problems in, for example, galaxies formations, or does it fit with the observations, for example, from gravitational waves merger, things like that?
Yes. We did the estimation of the number of black holes. The model depends on the rate of black holes that are formed or emerged, and we were based on the star formation rate for this from Alleviating H0, and then with some assumptions we built the model taking these astrophysical parameters of how many black holes are merged, how many are binaries. But what you said, it's very interesting that with LISA, for example, that and with much more data from the multi-messenger astronomy, and if one has a much better distribution of the black hole mergers, then the model will be much more constrained or falsified. So if because it depends on the black hole on the black hole mergers. So if we have much more data from the actual black hole mergers from gravitational waves, then the model will be much more constrained.
Yeah, thank you. Because I think you cannot treat alpha in your model because you need alpha to be such values to resolve these problems, right? But if the alpha is too large, maybe it means that there are too many mergers, and yeah, I don't know, maybe it will cause problems.
If we have a direct measurement of the distribution of black hole mergers per redshift, that hopefully we will have from LISA, and then the model will be really constrained or maybe falsified, because now we are based on the star formation rate, and from that we'll build the distribution of black hole merging rate. So I agree with proper data for black hole mergers, things will become much more clear.
Thank you. And my second question is about the logic of the research. So you kind of you use kind of thermodynamics equations and derive Friedmann equations. So you kind of like also borrow the analogy from black holes, thermodynamics, and try to combine them together to form this kind of new theory. And my question is, okay, they are kind of similar. They can also be explained in thermodynamics. They can both be explained in thermodynamics way, but are they really, how to say, physically connected or just analogy?
That's an interesting question. How the apparent horizon is topologically linked with the black hole mergers interiorly. This is an assumption, the basic assumption of the model, and but it's also close to, or based, it's very close to the holographic principle that the boundaries encode what happens inside the bulk. So we are based, our main assumption with a topological link about the apparent horizon and what's going inside. This topological link is based on the holographic principle that what happens inside the bulk is encoded in the boundary.
Okay, thank you.
Okay, let's thank the speaker again.
Thank you very much.